Good morning, everybody. I hope you're all well. Eduardo, I was trying to unmute you to see whether my microphone is working. So hopefully that's
Yes, it's working well.
fantastic. Fantastic. Thank you. Right. Yes. Good morning, everybody. Good afternoon. Good evening, and to those in the Americas who join us today. My name's Stefan Stimson, and I welcome you to our fourth APAC webinar. And I'm the Business Development Manager for RBR in Asia Pacific. So I've dealt with some of you already, and I look forward to future dealings. I'm based in Hobart, and just south of Hobart here in Tassie. And in the spirit of reconciliation, RBR acknowledges the traditional custodians of country throughout Australia and their connections to land, sea, and community. And I pay my respects to their elders, past and present, and extend that respect to all Aboriginal and Torres Strait Islanders people today. Today's webinar, we're jumping across the ditch from Tassie over to New Zealand. And I'll shortly be welcoming Eddie Beetham of Tonkin Taylor in Auckland to present today. And no doubt he'll show photos which will make me even more frustrated that we're stuck at home and not able to travel to the wonderful Pacific. All our webinars are recorded, and I should be recording this one as well. So I believe it is. And that's good. And there'll be time for questions at the end. But by all means, Eduardo, you heard earlier, his dulcet tones. He'll be available to answer as we go, as is Dan in Washington and RBR China. So let's get this underway. If you haven't already muted your microphone, if you can do that and turn off your cameras, then that will save some bandwidth for poor the bit of string out of Tassie. We'll cope. So RBR is a Canadian manufacturer of instrumentation. They're high accuracy, WOS standard, very low power, and we split them up into four categories. Sensors, which are basically instrumentation which can go onto our own loggers or third-party loggers to measure dissolved oxygen, temperature, conductivity, etc. Loggers are actually the instrumentation that brings it all together. So the sensors attached to that, and it's got power and memory inside, and it can control it. And then we have an area called systems, and that's basically a way of getting this oceanographic data or data from the seabed or the mooring out to the surface and out to the wider world. And that may be an inductive modem through our Cervelo with data storage and Iridium, etc. And then we also take our existing products, such as the conductivity sensor and pressure sensor there, and we have a oh, sorry, something's happened there. Hopefully that's better. And we have a lost my train of thought there. Yes, so we have the standard products onto OEM platforms, so they may go onto Argo floats, gliders, etc., used for integration by third parties. So let's move on. So if we have a look at the standard range of sensors that we have, instrumentation that we have, on the right-hand side we have the sensors. There's a temperature and depth and our dissolved oxygen sensor. We move along to the more capable compact logger. That one's just temperature, but we have a whole range of sensors in the compact logger range. We then move into our CTDs. The Brevio you see there is a small version of our CTD. It's got half the amount of power capability, but it has the same accuracy, same memory, just a smaller form factor. And then we have the bigger CTD. And then the Concerto can have 2 extra channels added to it. So it's a 5-channel logger. So you may add turbidity, dissolved oxygen, PAR, whichever tickles your fancy when we build it. And then the big brother, the Maestro, which is a 10-channel instrument, so we can bulkhead and cable mount a number of sensors up to 7 in addition to the standard CTD. So that's just a small part of it. One of the things that amazed me when I joined RBR earlier this year, after 15 years of being a rep, was exactly how wide the area is. So there's just a small selection of the instrumentation that we provide, and it includes a software which is either for PC and Apple, Mac, or actually for mobile devices as well, right through single channel compact loggers, battery systems, comm systems, and then in the bottom left corner, we've got a couple of the integration options. One is a wire walker, which we'll be talking about next week, and the other one is the SOFAR Spotter Buoy smart mooring, where you can integrate our Coda loggers, sensors, sorry, into their mooring and bring it up to the buoy and transmit it out to the outside world. Today's talk, we're going to be talking about depth loggers. So I'll just give you a bit of an overview on the compact and standard depth loggers we have. The yellow ones are the compact loggers. Single channels are Solo, 2-channel is the Duet, and then the standard loggers are the Virtuoso and Duo in the same mechanics. So what happens is you can have the standard D. It looks like a lot of words, but it's actually quite simple because they're all the same. The standard D is a 2 Hertz maximum depth sensor, and then you can have Tide 16, which is tide firmware on there, up to 16 Hertz sampling. Wave 16 has wave firmware in there, and then Fast 8, Fast 16, and Fast 13 are just depth loggers with a maximum of 8, 16, 32 Hertz. That's the same in the Virtuoso. It just has more power and more memory, and some connectivity advantages. And then each of the models are also available in a 2-channel model, the Duet and the Duo, in exactly the same way. Just has a temperature thermistor on there as well, and the temperature is available as a standard 1 second thermistor response time, or a 0.1 second thermistor. And then the standard models go up to 1,000 meters for the yellow loggers and 750 for the white loggers, but we have titanium versions as well to take you up to 10,000 meter range if you need to. The compact loggers specs are shown there. So the main things to see is that the yellow compact loggers have a single AA battery, and the standard loggers have 8 AA batteries. And that can be any battery chemistry as well. The calculations I've used there are with lithium thionyl-chloride, which give us the best performance, but you can actually go through alkaline, lithium ion, etc., even rechargeable batteries, depending on your measurements. The performance changes over that period. The accuracy of them is 0.05% of the full scale, so it's important to choose a scale which is as close to your operating range as possible to get the maximum accuracy out of it. And then the white loggers have the options of twist activation, so you can set it up, turn it on and off by turning the end cap, external connectivity, which I'll talk about in a little while, and Wi-Fi is available on it as well as an upgrade. So you can actually, rather than opening up the end of the logger, plugging in your cable, you can actually connect to it via the Wi-Fi on your phone or on your laptop or computer, and download the data. Less useful for these sorts of instruments and deployments, because you normally leave them for a long period of time and then download them and have to change your batteries and desiccant. But it's available and very useful if you're profiling or accessing data quite frequently. So I've given a couple of examples of endurance there. If you decide to set up either of these instruments at 1 Hertz on a single lithium thionyl-chloride battery for the Solo and 8 with the Virtuoso, you can get over a year's worth of data at 1 Hertz. That's a lot of data over that period. If you want to work at 16 Hertz, and I've used this deliberately because Eddie's presentation today is based on the 16 Hertz sampling, You can get about 44 days with the Solo, and that's limited by the battery. There's still memory left, but the battery is used up. And with the Virtuoso at 16 hertz, you get over 3 months, and that's limited by memory. You still have 165 days of spare battery. So in actual fact, using the top tip from last week, you can actually redeploy it if you wish on the same batteries once you've downloaded it and cleared the memory, and get another 3 months out of it. And then with bursting, which is again something Eddie will be talking about today, you can't burst with the compact loggers, but with the Virtuoso, I've given an example there of a burst of 4,096 samples, which is about 4 minutes worth at 16 hertz. Doing that every 15 minutes, you'll get 11 months of data. And again, that's limited by memory. These are only just some examples. They're extremely configurable, and I encourage you to use Ruskin to try different settings to see what it's capable of. Just as a review from earlier webinars, having a look inside the logger, you unscrew it at the top. There's a double O-ring at the top to prevent water going into the logger. And then inside with the Solo and the Duet, you have a single AA battery. It tells you which way to orientate the battery. And there's a place there for desiccant. And as you can see by that desiccant, which is a little bit pink, it needs replacing. As you roll the logger over, there's a USB-C connector for it, and the cable comes with the logger. And these instruments have been completely redesigned from the last model, so they're true USB speeds. So it's very fast to download. As you can imagine, some of the data files are quite large. Going to the bigger form factor, the Virtuoso, and it's the same with the Duo. There's 8 AA batteries here rather than a single one. 240 million readings. You have the the red end cap. You can twist to turn it on and turn it off. And I've mentioned the Wi-Fi connectivity as well. All of them are ready to go if you either buy it up front or you can upgrade it at a later stage. Inside the logger, you take off the red end cap, and again, the electronics are protected there. And you can see there's a battery to the top left. There's a battery compartment, and the 2 connectors there. There's the USB-C on the top side, and then there's a mini data port to connect to either your external connector on your end cap or to a SSM for inductive modems, etc. So there you go. If you open up the batteries, it accesses the batteries there. You slide them in and then close the cap, and you're ready to go. And there's the end caps, which the standard red one with the desiccant in it, and also that's actually a titanium one for the deep water model. But you can see the connector on the end side, so you'd connect your mini data port cable through that, and you've still got the desiccant as well. Okay, I didn't think I'd ever have to do this with the webinar series, but we mentioned it last week with Giles with his hydrographic presentation with the TGRs 1050s, and I'm also just going to mention in passing the TWRs, the tide and wave recorder. This is our first generation of logger, and you can see that it's got a DB9, I think it is, serial port, and it uses CR123 batteries, and rather than the measurements we have where we're talking about with the Virtuoso 240 million readings, this had 1.4 million, so it's a significant growth that's happened over the time. But I mention it now in passing for 2 reasons. One is Eddie will be talking about it today, and also because there's a program I'll talk about at the end. So you've got that. So just quickly whizzing through the top tips. Our first top tip at the first webinar was about the auto deploy, auto download, auto stop functions. So you can have a look at that on Hannah's webinar, which is on our website. We did the using Ruskin as a planning tool, which lots of people have contacted me about since and said how useful that's been as a tool to play with. And I encourage you to download Ruskin if you don't already have it. Last week, we talked about the fresh battery. And again, that's useful if you connect, put a new battery. If you press click, the generation 3 loggers will remember when you did that, how many samples have been taken, and do an estimate of how much battery is left to maximize that. Steph, sorry, I've got a message coming through from Eduardo. Today's top tip is about reviewing and exporting data from Ruskin. So there's a couple of ways to do that. The arrow is when you plug in your data and you download it, it comes up at the bottom of the screen. This has obviously got a lot of parameters on there. It's got speed of sound, salinity, sea pressure, turbidity. It's a multi-channel logger. The button, which is, I put a big red arrow on it to make it easy. If you press that, that actually exports the graph. So you set up the webinar, the file name, where you want it saved as a PDF, and it saves it, so you can put it straight into your report if you want. With Ruskin, it's very configurable. You can change which parameters are shown so that it doesn't have a whole load of axes shown and a very small area of graph, so you can change it all beforehand. I just wanted to show you this as an example. We also have, and Eddie's an expert on this, is you can, once you've got the data set, you can see it's highlighted blue, and you right click it. You can either close the data set or you can export it. And Ruskin is a SQLite file format, so you can easily read it. But you can also export it into Excel as a text file, into an Ocean Data View spreadsheet, and as a binary file. And if you are taking these, some of these files are very large, particularly the wave data that you're using. And so taking the binary files and processing them in something like Matlab, we've tried to make that easy. And on our website, there's a link in the middle here. I'm going to use my pointer to download RSK tools for Matlab. So these are actually tools which we've written and provide free of charge to you, freely available, and it allows you to do up to 50 user-facing functions within Matlab. I'm certainly not an expert in Matlab, but I know a lot of people use these readily to handle their data and start doing very simple things, from despiking to smoothing and taking out outliers, those sorts of things. There's lots of information on our website, and you can either do it through products and software, or there's the link at the bottom there you can go to. I'm nearly done, so Eddie, if you're warming up, mention a couple of upcoming webinars. Next week at the 2 a.m. Australia time, 4 a.m. in New Zealand. Tamara Schlosser will be talking about coupling, the coupling between subsurface irradiance, chlorophyll, and seal vertical migration in the Bay of Bengal, I believe it is, and that'll be very interesting to rerun. Obviously, the title hasn't changed on there. I do apologise for that. This time next week, myself and Chris Contos, hopefully, or possibly Drew Lucas from Delmar Oceanographic, will be presenting on the wire walker and using waves and power efficient loggers for autonomous profiling. It's different to what was presented before. It's based on a scientific paper which was submitted to a seminar, and so we're presenting that for interest. And then the following week, to sort of wrap up the APAC series on a weekly basis, we're going to have something which is quite exciting, and I encourage you to join. We may change the name of it, but basically it's Ping the President, and it's our president, not the US president. And it's about getting the most out of your RBR instrumentation, and it'll be in a format of a Q&A basis. So it'll be very relaxed and very informal. And we find the conversations around these webinars far more important than they just presentations. So I'll be chairing it and interviewing Greg, and we'll be asking him some questions about changing O-rings, about deploying it, getting maximum life out of your batteries and those sorts of things, which batteries you can use. So it's a really good opportunity to listen to some of the questions being asked, but also use it as an opportunity to ask directly to Greg. He knows the company inside out, as you'd expect, but far more than you'd expect probably. and I certainly encourage you to come along to that. So that'll be a nice way to do it. And then finally, the pay it forward incentive. So given that the last two presentations, or last week's and this week's, include very old loggers, I'd just like to remind everybody that until the end of the year, we're running a pay it forward incentive, which has now been expanded as well to include not only old generation 1 RBR instruments, but some of the older Seabird instruments listed there. You can also donate to a local non-for-profit organisation such as a school. Here in Tassie, we've got a marine research centre which does school programs, and instruments have been donated to those sorts of organisations. And if you do that, and we'll discuss the details of it, you actually, on top of your quantity discount, you get a 20% discount on a like-for-like instrument. So if Eddie, for example, donates his TWR 2050s, he'll get a 20% discount on the equivalent now, which will be the Duet D-Wave. There's lots of information on our website for that, but by all means, contact us to do that. There's my details. One thing I would mention is that after this, as you know, I follow up and contact you, and in there, I always encourage you to reach out, and quite a few of you are doing so. I don't just put that in there as a marketing blurb. I genuinely mean it. We really enjoy hearing from you. One of the people online today, Laurie Hughes from Griffith University, I actually sold my first instrument to him about 15 years ago when I first moved to Australia, and we're still in contact, and we're big believers in long-term relationships. So it's not about trying to get a sale out of you today, it's about building relationships. So I genuinely encourage you to make contact with me. I'd love to learn about what you're doing with your instrumentations. And also, we develop instruments. We don't make these for ourselves, we make them for you guys. So if there's applications you think would be useful to for us to look at, then please contact us. We're all ears. So you'll be pleased to know that's the end of my bit, and so I've done the stop sharing bit. Now, Eddie. Is Eddie?
Good morning.
Good morning, Eddie. Nice to see you and hear you again. How's life in Auckland?
Oh, life's good in Auckland. We're still battling the COVID situation here, so still a few restrictions in place, but I guess that's the story everywhere in the world at the moment.
Oh, awesome! And you're a coastal engineer based in Auckland at ex-Auckland University, and now with Tonkin and Taylor in Auckland. How did you get into the coastal engineering field?
Well, I'm a coastal scientist, I guess, not technically an engineer. So I kind of just fell into that by through university, studying environmental science and geography, marine science, type papers, and just growing up as a surfer and then observing waves and how the beach moves around, and just piqued my curiosity. So when I was studying all this stuff, it made a lot of sense to me, and it was really interesting, and I could see there's lots of problems that exist at the coastline, and it was just a way to work with some really interesting people and work on some interesting projects that enable you to kind of think strategically, read the landscape, measure stuff, try model stuff, and just at the end of the day, hopefully solve some of the problems where humans and the coast are interacting.
Yeah, it's amazing. Everybody I meet in this field doesn't just see it as a job. They all have this passion which has been in there for a very long time, which makes you good engineers and scientists. So apologies for that oversight. Before you start off, Eddie, as we do at RBR, we'd be really keen to learn a fun fact about you that maybe your colleagues at Tonkin and Taylor don't know about you even. Have you got something to share with us?
I've been thinking about this one, and to keep it lighthearted, I guess. Well, growing up, I always thought I'd be a professional soccer player, or do something in that kind of football realm. It was quite a strong passion and obsession until I was about 15 and I got my first surfboard. So that's when my career trajectory shifted towards the coast, and professional surfing wasn't really on the cards. So a coastal scientist seemed like the best thing to do.
That's awesome. Well, as a soccer nut who stopped playing only last year, I love that story. So that's a great way to lead into it. So I'll stop sharing my my video, and I'll hand it over to you, Eddie. Take it away.
All right, I will share my screen. Share.
Perfect. Yep.
I'm going to share the screen. Hopefully. Now, how do I make it full screen?
So if you click on the bottom right, the icon like you're starting, there you go. Perfect.
Nice. Just needed to get rid of my face on the video. So yeah, as Steph introduced, my name is Eddie Beetham. I'm a coastal scientist at Tonkin Taylor. So we do a lot of work throughout New Zealand, Australia, and the Pacific, solving all problems that relate to the coast, coastal hazards, and coastal management and that kind of thing. So the talk I'm going to present today is based on some of the work I did at university as a PhD student and then a postdoc, and then try and link that to some of the projects that I've been working on as a consultant, and how this is it's all in the context of understanding wave processes on coral reefs, and the aim of a lot of the research and the kind of work that I'm getting into is understanding the impacts of future sea level rise on coral reef coastlines, and in particular the atoll nations such as the Maldives, Kiribati, Tuvalu and Tokelau in the Marshall Islands, where the only inhabitable land is low-lying sandy or rubble islands that are built over the last 5,000 or so years through the accumulation of sand and gravel. All that material is transported by waves, deposited in kind of points of accumulation, and over the last few centuries have been inhabited by people as well. So these landforms are located in the middle of the ocean, surrounded by coral reefs, and really exposed to the risks and hazards associated with climate change and sea level rise. So the atoll nations and reef coast countries, or kind of coasts with fringing reefs, are often cited as being among the most vulnerable countries or communities facing increased sea level. And one of the reasons for that is that coral reefs are really effective at breaking and dissipating ocean wave energy, and they provide this natural breakwater structure that protects reefs from the kind of high energy waves that exist in the ocean. And some quick facts on this are that there's a lot of global review type papers come out in recent years trying to quantify the effectiveness of reefs as a disaster risk reduction type structure, and they come up with values like 100 million people worldwide receive benefits and flooding mitigation from reefs, and in the orders of the reef protection mechanisms and flood reduction are in the order of $270 billion. So that's some of the context for this research. So the approach to studying a problem like this, I guess vulnerability and exposure to sea level rise can be studied through many different lenses. And the way that I'm approaching this through a coastal science lens is to understand the physical processes that influence hazards that could impact islands and communities. So these are flooding and erosion, and the main drivers for kind of destructive flooding and erosion on a lot of these reef coastlines are waves. So waves typically dissipate the energy across the reef, and only under storms or extreme conditions or very high tides pose a hazard. But if we think about future sea level rise, the breakwater effect is likely to be compromised. So greater energy might be received at the shoreline, and it becomes a problem of understanding how much energy might change, how much more energy might be received at the shoreline, and what impact does that have on wave run-up, erosion, overtopping, and flooding. So the approach that we've taken to study this over the last, this is going back over the last 8 or so years, is to collect some really high quality field data and then use that data to understand the present day processes. So what are the important processes? That how much energy is reduced over the reef? How does that vary in different settings? What surf zone processes are important? And what kind of combinations of high tide and large waves produce the greatest amount of run up at the shoreline, or overtopping or flooding or erosion. And the next step is to develop confidence that we can numerically model these present day conditions. And that's important because we're focused on what's going on in the future and want to use some of this research to inform hazard scenarios and coastal hazard management. Then we need to be able to say with reasonable confidence how sea level rise in 50 or 100 years might change the wave processes and change that hazard landscape. So developing a numerical model confidence is really important in this type of work. And then once we're confident that we're representing the right physics and getting some interesting outputs, then we can get quite carried away in modeling future scenarios, whether that's at the scale of a specific field site that we use as calibration data, or exploring a more generalized approach where we can vary any scenario we want within reason and then get some more generalized outputs. So just quickly introduce a few of the key processes that are involved in this work. So this is a numerical model output, but I'm just using it as a conceptual diagram to show the important wave processes that I'll be talking about in the next few slides. So here we've got a simplified coral reef with a steep slope and a flat reef here. This is an abrupt transition to a flat, or quite a steep sloping shoreline, and then the island surface up here. And this is our wave profile. So this is a wave in deep water where it's quite symmetrical. And then as we come towards the reef edge, it starts to gets really asymmetric and steep and starts breaking. And then you can see this blue line dissipates on its way towards the shoreline, and very little wave energy is shown here. But so that's the dissipation of what I'm going to probably be calling gravity waves or incident frequency waves is one variable we look at. But we also look at how the dissipation of this kind of the visible surfing waves drives two other really important processes that influence wave run-up. The first is wave setup. So that's in the green line here, you can see this is the mean water level. So across the reef, this mean water level increases. And that's typically in the order of, well, you'll see some results soon, but typically in the order of around 5 to 30% of the offshore wave height. So that can be quite a significant increase in depth across the platform. That's due to the presence of breaking waves and that transfer of energy from, as the waves reduce in height across the water, there's a piling up of mean water level across the platform. And that's a process that's well known and well studied on sandy coastlines, and in the last few years has also been well studied on reef coastlines. The other process is infragravity waves, or surf beat, which you can see in these time series plots here. So this is just 300 seconds of the wave profile. That's what our pressure sensor data might look like before we've processed it. Located at this offshore location at the reef edge and at the shoreline. So you can see the incident waves in the blue line, really high frequency every 10 to 15 seconds. And then you see this undulating red line. And by the time we reach the shoreline, this undulating red line is much more pronounced than the blue high frequency lines. So that's a process where waves approach the reef edge in groups. You could think of them as sets coming in. They start breaking on the reef edge. The individual waves dissipate most of the energy across the first kind of 50 meters of the reef flat, but that wave group creates its own surge that passes across the reef flat. There's there's a few different mechanisms for the formation and propagation of infragravity waves, but you'll see throughout the, won't get into the details, but they're an important process that influences wave run-up, because typically the energy of a surge at the infragravity wave frequency can oscillate the water level in the order of 0.5 meter to maybe 1 meter under kind of storm conditions. It can be much more serious than that during cyclone conditions. but this surge in water level has a really pronounced influence on run-up on reef shorelines, and it has been known to be the cause of overtopping and flooding events as well. So the balance of these three processes is an important context for some of the data that we collected. So for my PhD, I teamed up with a team at SPC in Fiji, Jens Kruger, and a few others as part of the WACOP project, Waves and Coasts in the Pacific. And we deployed 3 sensors across the reef here. This is Fatato Island in Tuvalu, so on Funafuti Atoll, right in the middle of the Pacific. The main population is based in Whakawhale here, and our field site is down here. So it's kind of representative of many higher energy, easterly trade wind exposed reefs in the Pacific. Really narrow reef flat, only about 100 meters from the reef edge to the shoreline, really steep down here. And we put 2 rbr sensors on the reef flat, so the old 2050s that we mentioned earlier, and one right by the shoreline and one as far seaward as we could without getting destroyed by waves. And we also had we initially had an AWAC deployed offshore, and then we swapped that out for a Virtuoso halfway through because of the battery life was a lot more efficient. So it's quite fun mounting instruments. I'll just play this video, hopefully it works. So we deployed these sensors by drilling bolts into the reef and then attaching frames that the sensors sit inside that little casing because they get hammered by rocks moving around and other things. But you can see in this video, even under, this is about as calm a day as it gets, but it was a neap tide, so the low tide didn't fully drain off the reef, and even under those pretty mild conditions, it can be really tricky to deploy in these types of environments. So we actually collected data for about a year on this site, which involved some of the SPC team flying up every few months and swapping out batteries because of those old sensors that don't last quite as long as the new ones. And also to measure some beach profiles and see how things were changing. So this data was really interesting because prior to this deployment, there'd been a few studies that documented waves breaking across the reef crest and documenting how much energy was lost, and a few other studies documenting how much energy was lost from the reef crest to the shoreline, and not many longer studies that showed how wave energy goes from deep water and how that dissipates across the reef edge and right to the shoreline, and what that kind of the whole story of the reef, had it really been documented across a range of different conditions and not so in this kind of particular context of atolls. And so here's some of the outputs we get from the loggers. We have a burst. I think for this project we were doing a burst every 2 hours to collect 35 minutes of data at 2 hertz on the old instrument. So then once we get the pressure signal from the raw data, we correct the atmospheric pressure offset using an atmospheric gauge that is on the main island in Whakawhale, and then we de-tide using a de-trending tool, and then we calculate the different wave statistics using I typically use a zero down crossing method where we can split that high frequency signal into individual waves and then look at each wave and then calculate statistics of that. And also use a spectral filter to separate frequencies associated with incident waves and infragravity waves. So the idea of this was to look at across the spectrum of conditions that we measured, and this is just a sample over 2 months during the higher energy winter conditions, how those 3 different wave processes behave, and what the tidal controls were on how much energy is received at the shoreline and how those processes occur. So if we look at the blue line, it just shows the offshore wave height ranged between 1 to 2 meters, and we had a few different kind of swell events or local storm events where energy was a little bit higher. And then most of that energy dissipated across the reef fit, and you can see that zigzag is showing the tidal controls. And interestingly, there was always waves reaching the seaward sensor on the outer reef fit, but there were periods when no waves were recorded at the landward sensor closer to the shoreline, which is this one here. So as expected, there's this tidal control showing at lower tides we get much less energy at the shoreline, the reef fit and at the shoreline, and conditions that promote the highest waves at the shoreline were either high tides or slightly lower tides, but with larger offshore waves. And that modulation's partly because we get the inverse relationship when we think about wave setup, which is denoted by this little symbol here. So at lower tides, we get maximum wave setup. So that's the increase in mean water level is maximum at low tide because we get more intense breaking and more dissipation. And it's compensated by a higher wave setup. And as we go towards higher tides, the influence of wave setup decreases both at the shoreline and at the reef fit. But then when we look at these surges that are responsible for or influenced by wave grouping, there's no real pronounced tidal control. So it's kind of a pretty much similar wave height, similar for gravity wave height at the reef edge across the tide, but there is a control with offshore wave height, which is shown in the color. Also important that there's an increase in infragravity wave height across the reef as you go from the outer reef flat towards the shoreline. So that was kind of a new finding from this research that was a little bit different and just causes something to think about. So that was the first stage, is just presenting what's going on at the present day, trying to understand using the field data what's going on. So the next step is, once we've got this really cool field data set, can we represent that numerically? And that's important because first, with the goal of understanding the impact of future sea level rise, we can't wait around so we can measure it. We need to start making some predictions. We can create empirical relationships based on field data, but it's nice to be able to represent the physics of what's going on and then use that as an exploratory tool. So I used a fully nonlinear Booster-Nest model to replicate all of the field conditions that we measured over 2 months, and this is just showing the measured versus the modeled output for the time series at the offshore location, at the reef flat for these 3 different wave processes, and at the shoreline, in a comparison with measured and modeled outputs on the color plot here. This is really encouraging because it shows that we could accurately represent the main wave processes that are of interest to run up and overtopping and erosion at the shoreline. And we could do that over a range of offshore wave height conditions in a range of tidal conditions. So that first of all, that was useful because it gave us more insight about what's going on at present day. And it shows that we can use the model to understand wave run up, so we can model for a particular event and then extract the point of maximum run up and then calculate the processes that are contributing to that wave run up. So this just shows, like, over the tidal curve, the processes that influence run up change from these lower frequency waves set up in infragravity waves to the higher frequency incident waves as the tide increases. And it also shows that waves reach the shoreline for a lot of the time, so 71% of the time, but if we were just looking at the mean water level from tides and setup, it's only 25% of the time. So adding the modeling component and having that field validation gives us a really powerful tool to explore some of those less measurable processes. And then we can get quite carried away with what we model after that. So this is showing for different wave conditions, we can just increase sea level from present day low tide right up to 1.5 meters above present day high tide, which is around 1 meter, showing in the shade here. And then we can see that transition continues into the future, where we get this kind of trade-off where we have present-day conditions, kind of a balance of these mixed surf zone processes at the shoreline, and then in the future we'll be mainly dealing with less surf zone processes and more of those incident frequency waves with less dissipation. We can also look at the threshold for waves overtopping under these different offshore wave conditions, and this shows for swell waves that you'd expect on this island every year to be 35 centimetres of sea level will result in annual overtopping of these conditions, and for storm waves that occur every year, 30 centimetres of sea level will result in annual overtopping under those conditions. So one complexity of coral reefs is that they're not static systems. Reefs are hopefully covered with lots of coral and coralline algae and other calcifers that grow and kind of continually adjust and add to the reef structure. So that's another complexity that we can start exploring using model tools as well, where we can not just adjust the sea level, but also adjust the reef elevation and have a look at how future trajectories of reef accretion or not result in different behaviours of wave interaction at the shoreline. So this example shows that a scenario of sea level rise when there's no reef accretion, as you increase sea level, mean sea level, and into the future, we start getting overtopping depths right at the crest that are quite considerable and potentially would be really hard to cope with. And compared to where we have full accretion at the outer reef at the same rate as sea level rise, we can mitigate that magnitude of overtopping quite considerably. So that the outcome from this work was that if you can protect the reef and maintain a healthy reef ecosystem, you have much more chance in mitigating some of the impacts of flooding and erosion with higher sea level. But there's some complexity with that as well, because while we're dissipating some of that wave energy that would increase otherwise, we're not adjusting the height of the island, so the threshold for overtopping is the same. So there was not actually much gain in offsetting the time or the threshold and when overtopping would occur. The gain was only in reducing the magnitude of the overtopping. So we got to do some pretty interesting stuff just based on that one field site. So the next stage of work was to expand this into something that's more generally applicable, because realistically, there's hundreds of communities in the Pacific. The reef structure is a little bit different. The wave exposure is a little bit different every time, and it's not really feasible to go and measure everything. And it's not always feasible to do detailed modelling everywhere either. So I tried to run a whole bunch of simulations where we could vary the width of the reef, the depth of the reef, the height of the island, offshore wave height, offshore period, and a whole bunch of different scenarios, and try and develop a conceptual model of kind of island exposure to wave overtopping, which is measured by the depth of overtopping at the crest. So the result of this was this kind of conceptual model summarized in this formula, where we've got two dimensionless variables, relative reef width and relative island elevation, simple parameters that are easily measured, so the width of the reef divided by the depth of the reef, and the height of the island above the still water level compared to the offshore wave height. And you can see the markers show where flooding occurred in the model, or overtopping occurred, and where there's no markers, it shows where there was no overtopping. And comparing this to documented events where there was high wave run-up but no overtopping, compared to where there was overtopping or kind of destructive wave-driven flooding, seemed to then pretty well with documented events throughout the Pacific. So this gave us some confidence to explore trajectories of vulnerability and see how different islands, based on their morphology and wave climate, could be exposed to future sea level rise. So here if we think about the impact of sea level, we're changing the reef depth and we're changing the relative island height above the still water level. So our exposure trajectory goes from mean sea level, where we're in the white zone. And then as we start decreasing on both of these axes, we start curving towards the threshold and under different offshore wave climate scenarios. So I think this is a 1 in 100 year event, or a 99% exceedance event, and we start entering the kind of inundation or exposure zone. And the deeper we go into this kind of darker blue, the more the hazard level increases. So that was just a way of kind of showing that we could try and conceptualize the kind of vulnerability trajectory based on simple wave climate and morphology characteristics. And that was all possible because we had kind of stepping it quite far back, but the confidence that we gain is by relating everything back to the fact that we've got a field validated model that was able to represent the physics of the surf zone processes that we're interested in. And then you can, after that, you get kind of enough confidence to get a bit carried away with how far the research can go. So I guess the main summaries from this was that future sea level rise will change the nature of wave transformation on coral reefs and a shift away from those surf zone processes of wave set up and gravity waves towards those kind of typical surfing frequency waves. And that's important for understanding the landscape of wave run-up and the type of wave run-up that causes flooding and hazards. Sea level rise will have a double impact on reef coastlines. Firstly, the increase in depth over the reef will allow larger waves to reach the shoreline, unless that's compensated by future reef growth, and that's a topic that we're still researching. Although climate change will also have pretty severe impacts on coral reefs themselves. And the other impact is that sea level, as you increase water level, the freeboard of the island decreases as well, so less wave height or less wave energy is required to overtop the island. And we're also doing some work at the moment looking at the morphological response of islands to overwash, and some of that shows that as waves wash over the island, the sediment moves around in a way that the island freeboard actually does adjust, and it can keep up and grow with sea level, but it does move landward at the same time. So that's a topic for another day. So the idea of all of this is that we can develop a pretty comprehensive understanding of the coastal processes and use that to understand the coastal hazards on these reef systems. And one application of that is we input this conceptual model of kind of wave flooding risk from the previous work here into an early warning system for looking at exposure to flooding during cyclones in Fiji. So this is simply looked at the offshore wave height across the fringing reef zone here, and then flagged what the height where wave exposure might reach at the shoreline. And that's built into a wider flood risk model that colleagues of mine at Tonkin Taylor developed. So that's the main story over for me, but I just thought I'd show some other photos of deployments that I've worked on. So a couple of years ago, did a project in the Maldives where we measured wave processes throughout Hooverdu Atoll. So that involved putting the old 2050s out again because no one else seemed to want them, so I could leave them on the reef for a year out at the reef edge here, and on a bunch of smaller lagoon islands throughout the atoll as well. So this was looking at how wave energy transforms across the atoll reef, but also passes into the atoll to affect some of the smaller lagoon islands that exist in those settings. So this is, and for these deployments, we basically wrap the sensors up in kind of electrical tape, write a little tag on them so the locals don't steal them, and then just strap them to the reef. A section of bare reef rock with cable ties, and it seems to do the trick. We had one sensor go missing, and a local kid had taken it, but our contacts were able to track them down. So that's why we've got the little markers on, telling people to please don't touch them. that's what they look like when you're pretty happy to fly halfway across the world and pick it back up again 3 months later. And we also had an acoustic profiler offshore with this is a solo rbr solo recording alongside it, so we got a nice comparison between the two types of sensors. The rbr sensor was great because it could burst every half hour for 6 months or 7 months, and the directional wave gauge could only burst every 4 hours. So we got directional wave data for every 4 hours, but in the meantime we got much higher frequency wave heights. That's what it looks like after 6 or 7 months out at sea. And so it's just a really quick highlight of that data set, showing how you get this nice directional spectra and kind of transfer from swell dominance to wind dominance as you go from the offshore across the atoll rim and into the lagoon islands. So just quickly, I know we're running short on question time, but a project that we've worked on recently at Tonkin Taylor was measuring wave and weight processes in the downtown harbour. And this project was interesting because we kind of rapidly, we wanted to collect a month's worth of data, and we were due to pick up the loggers on the 1st of April. But New Zealand went into lockdown on the 26th. So we couldn't collect them, and they were stuck for an extra 2 months. I'm not showing the full data set here, but you can see that as we go tick along, pretty much business as usual. I think about here we had a ban on cruise ships, and then as soon as we went into lockdown, you can see wave height dropped by half because we had a rule in New Zealand where no vessels were allowed underwater except for ferries, basically doing essential service travel. And so the impact of those restrictions was really evident in the data, and it does keep going. And one of the loggers laughed. We had a virtuoso out that collected data the whole time, so that was a pretty interesting little side to loggers stuck in lockdown. And so yeah, that's it for me. A few research papers if you're interested, and otherwise I'll let you get on with your afternoon unless you have any questions.
Oh, that's excellent, Eddie. That's yeah, a lot of stuff you covered there, and really detailed. So thank you very much for that. And I was sort of blown away by the main presentation, and then just looking at that last bit on Auckland Harbour. It's amazing to see the effects that that COVID's had. So evidently with the lack of boat wash in Auckland Harbour. So that's great. I will open up to the floor for sure. I do have a question on more practicality. You've answered it about the locals tend to either don't find it or they respect the signage and bring it back, so you don't seem to have lost too many, which is great. But in terms of mounting them physically onto the reef, where you're using cable ties, obviously it's not doing much damage. Do you get much pushback from potentially damaging the reef by physically mounting it into the reef itself?
Well, we do our very best to not harm the reef. Of course, we wouldn't even mount anything onto a living structure or onto a living coral. So typically there's cryptic spaces on reefs where you can mount an instrument without causing any damage. I think the main risk where you could accidentally knock something off is just if you have to swim down and you're tying something up, you can always kick something with your feet accidentally. But no, I haven't heard any, haven't had any complaints with that approach. But yeah, we always try and be respectful of nature and the reef.
Sure. And do you get the speak to the local population and get them, to buy into the concept to help prevent investigation and removal of loggers? Yeah,
we do. But in Tuvalu, we made an announcement over the local radio station. We've got some of the local people that were hosting us to do that. Because people are curious everywhere, but the people in the islands, I mean, when you get visitors coming in, they don't know what they're doing. They're kind of stomping around, doing measurements, doing topo surveys and everything, you stand out, so people do get curious.
Sure.
And the approach we've found is it's always better to communicate what you're doing and try to include people. Is better than just kind of hiding stuff and pretending it's not there. So, and people seem to respect that. So talking to the village where you're staying, having local people that you trust is really useful. So we always have local people that can kind of communicate the local ways, you know?
Yeah, absolutely. Yeah, absolutely. So is anybody, the questions have been quite quiet in the chat. You've been obviously listening to Eddie in detail. Has anybody got any questions they want to ask through the open mic?
I might ask one. Is that all right?
Yeah, go ahead, James.
Hey, Eddie. Great talk, and I love the experiments in the violet. Really good. We've done very similar stuff ourselves. I like the graph that you came up with at the end with the turning point between the overtopping based on geometry and offshore wave height. Was there much sensitivity that you played around with the offshore reef slopes and then also the beach face slopes? Like, I know there's the Beware tool that's out there now based off X Beach, where I just wanted to know how much that sort of affects that overtopping rate, beach width, obviously.
Yeah, it is a factor that I looked into, and I ended up ignoring it because I wanted to stick to those really first principles that kind of govern the wider thing. So I kind of separated the components into primary and secondary influences, and I considered reef slope and beach slope to be, they're still important and they do modulate some of those processes. So if you get a steeper reef, you typically get more setup. So there are a few relationships like that. And I didn't account for them specifically, but they can be accounted for by tuning some of the variables. But it is important to consider for more local scale problems. But yeah, you're right, they definitely have an impact, but I considered it a little bit too complex to add them for the objective I was after.
No, I think for a first stage approach and for concept design things, it's a really good and useful graph, that one. So it's really, really good. Is your paper available as well?
Yeah, that one's open access. So
okay, cool.
Yeah.
Awesome, thanks.
Yeah, no worries.
Thanks for your question, James. Yeah, go ahead.
Thanks for the talk, Eddie. That was really good. Just the model you mentioned, what model was it, is the first question, and then the second one is just any of your views on factors affecting reef productivity in terms of generating sediments, whether that be reef health or wave climate, etc., and what that has flow-ons for the morphology.
Yeah, I guess, good questions. First one, the model I used it's a fully nonlinear Boussinesq model based on the Green-Nardi equations through the flow-solver basilisk. So it's basilisk is a kind of fluid dynamics program created initially at NIWA by a guy called Stefan Stimson. He now works at CNRS in France. So it couples the fully nonlinear dispersive equations with a finite volume shallow water equation for braking and run up. So it's open source, it's available. It's quite I guess it's not as operational and standard as an X Beach type model that basically gives you the same results these days. So this was actually some of the first, when I started looking into this back in 2012 and 13, there hadn't been much work using Boussinesq models on reefs. So I teamed up with some people I'd connected with at NIWA and kind of ended up using that model. But since then, there's been a lot of work validating similar tools, similar models, and they all seem to behave in pretty similar ways. So, and the other question on sediment, we've looked into this a little bit in terms of, I guess on reefs, there's two important mechanisms that can generate sediment. The first is physical breakdown of the reef structure. So that's from wave abrasion, breaking up branches and kind of abrading fragments of branch into eventually sand. That takes a very long time. And the other one's grazing from mainly parrotfish and urchins. And so your kind of natural abundance of, especially for sand-sized material, that's typically the biological erosion that's important. So the main ones will be the population and spatial distribution of grazers that bio-erode the reef. So they just basically chew on the reef framework and directly convert it into sand. So if you have heaps of urchins or heaps of parrotfish, then you can get quite quick turnaround in sand generation. But that feeds back into the wider a naturally healthy reef system will have that population balance in check.
Thanks a lot, Eddie. And so really that does reflect back on your talk, both on inundation and morphology, that just the importance of the reef health and both the particularly biological.
Yeah, absolutely. So we're doing some research now looking at coupling the whole process of morphological updating and sediment production and sediment transport using an X-beach type model that resolves the waves and sediment. So that's working pretty well as well. There's a reference in the slides about that paper.
Excellent, great question, Evan. I think unless does anybody have any pressing questions? We're over time, so I don't want to keep Eddie longer than necessary, but this is a great opportunity. We're getting lots of feedback saying how great your presentation was. So you've kept up that mantle that we've had with the previous presenters as well. So well done, Eddie. We really appreciate your time.
Yeah, I know it was. I felt a bit appreciated because listening to the few for the last couple of weeks they've all been really interesting. So yeah, hopefully I didn't ramble too much. No,
not at all. It's been excellent. No, we're lucky. The clients that we have are very specialised and love sharing their work, and it's really interesting work. So we really appreciate it when you come along and share this. So thanks, Eddie. Really appreciate your time, and I'll be in touch with you shortly. Anyway, this will be available online over the next 24 hours, and thank everybody for attending. We had another good turnout today, and lots of people watch it online. And hopefully we'll see you next week, and we'll talk about the Wire Walker, which is a wave-powered profiling body with the RBR loggers and inductive modem to bring the data up from there. So we'll see you all next week, hopefully. Thanks again. Stay safe.